Typically for us, we're going to work on binary search trees, right? Saying that everything to the left of a node is going to be smaller than that node, and everything to the right of that node will be larger than the node, right? So if we pick 8, right, everything on the left side, right, this subtree we call it, is smaller than 8, and this subtree is larger than 8. Make sense? If I pick any value, right, so once again, if I pick 6, right, 4 is smaller than 6, it's on the left subtree, and 7 is larger than 6, right? It's in the right side. All right. So when we talk about trees and binary search trees in our algorithms today, we have to talk about, right, the fact that smaller values go to the left, larger values go to the right. Talk about the fact that a tree is made up of subtrees, right? So you can apply an algorithm to an entire tree, but you can apply the same algorithm to a tree within that tree, right? Which lends itself well to recursion. And we have to talk about the first node is called the what node? The root node, okay? And so we always have to remember where the tree starts. Kind of like in a linked list, we always need a head, right? Where does my list start? Then I can get to everything. In the same way, we have to know where root starts, so I can get to the first node, so then I can get to everything. Because there's arrows everywhere else, right? Except for where in my picture today. For us, we know, well, we're going to need an arrow to it, right? AKA a what? A pointer. Right, hopefully. Oh, wasn't that one of the questions on the test? What does a pointer hold? And you say an arrow. Wasn't that one of the answers? I hope you didn't choose it. Right. So, just like in our linked list, we're going to make our trees class-based. So we're going to have a BST node, which you created on Monday. And then you're going to have a BS tree, which you're creating today, and we'll continue to use on Monday's lecture. And so, when we think of this class, where do I want to write this? I'm going to write it over here. I'm going to move. How does that sound, guys? To make a state-of-the-art podium, it's like, I don't want it.
I have to bring my neck left, so.
Right? So, class BS tree, right? Because your tree holds BS. Right? Let's do private data. We can do public data, but we'll do private data. So, the private data of our tree, right, needs, right, a pointer to the root, right? So if our tree holds nodes, BST node, right, star, and I should just call it what? Good. Please call it that. And then there's really not much else I need to keep, but I might want to do something like unsigned and right size. Sometimes it's nice to keep track of size, so I don't have to like search the whole tree and count all the nodes, right? That's just so if I want to get the size, it's easy. But really, what do I need to store in the tree? The tree needs to know where I start and possibly how big it is. Does that make sense? That's probably all that I need for my private data of my tree. Anyone think of anything else we might need? For the private data.
Probably the arrows where the children are.
Where all the children are, but see, every node knows who their children are. So the tree doesn't need to know about all the arrows. It's just about know about the first arrow. So I think that's all we need. Right? And when the tree is empty, where does that pointer point to?
Nope.
No, right? When the tree is empty. So if we add in our constructor, right? Our BS tree constructor. Right? I'm just going to write it here so we have it. Right? I probably want to set root to what? And set size to. That makes sense? And on the creation of my tree, root is null, meaning there's no values in my tree, right? Which means that size is what?
0.
So there's my beautiful picture, right? And so today we're going to look at insertion, adding values to my tree. Remember, we have to insert a certain way because in a binary search tree, smaller values have to go to which way? The left, and larger values have to go to the right. And if it's the same, we don't insert.
So then don't we check the value of root?
We could, but remember, right now I can't check the value of root because root's null. And if I check the value of root, right, what's gonna happen? Sig fault, right? Because if you dereference, so if you use the arrow operator on a variable that holds null, you'll always get a sig fault, right? So there's an order to what we're gonna do. So we're gonna set up our insertion algorithm. So we're gonna do insertion, we're gonna do traversal, so that's in order traversal, right? Because we said if you do in order on a tree, the values come out in what?
In order.
In order. Okay. Right? And then we're going to do clear the tree, delete all in the tree. And we talked about last class how that would be post order. Right? So we'll talk about those two traversals. So, can we come up with the 4 conditions for insertion on a tree? So there's 4 conditions, right, for insertion. So what does the tree look like? So if I go to insert a value into the tree, what is one possibility?
It's empty.
It's empty, right? So first possibility is it's empty. I would suggest that that is your first case because you always want to check for null first because once again, if you dereference null, what happens? It crashes, right? Sig fault. So you always want your first condition to be the check to make sure the thing's not null, right? Or it is null, and then go and work on other stuff. So one of your cases is that, right, the root is null, meaning the tree is empty. What other cases?
Value is smaller than the root.
Okay, the value is smaller than the root. So when the tree is empty, root's null, easy, we know where the value goes. Right? So one of your cases is, right, root points to null. So if I want to insert 5, right, it's pretty easy. Where does 5 go? Right there. Right, we'll do it in a different color. That way it shows kind of what's going on, right? So the root, right, gets 5 and 5, right, as a node, as nulls. Right, that's one case, right? Vinzel said it could be what? Smaller?
Smaller.
Right, so our tree could be this right now. Don't get that? Our tree could be that. So when I say insert 5, there is something there. It's not null. Right? There is something here, but 5 is smaller than what? 8. And so which way do I go?
Left.
I go left. And eventually you get to a point where that arrow is what? What does this mean? What value is this?
No.
No. So as you insert, right, you keep going, do I go left or do I go right until you find null? And once you find null, that's where you want to what? Insert. And so that's where 5 is going to go.
So in the insert function, you would create a node that points in 2 directions?
Well, our last lab, this is what we created, right? We created a BST node, and the constructor set left child to null and right child to null. So when we create it, that should happen. Right? So it can be smaller, or it can be what?
Larger.
Larger. All right, so here's 3. Right? If I insert 5, well, there's already something here, so which way do I go? I go right. Notice this time it's what? It's null, so now I can add, right, 5 in. What's the fourth case?
When it's the same?
When it's the same, right? So if I said insert 5, right, but my tree looks like this, right, then you don't perform an insert, right? You say insert 5, oh, 5's already there. Right, I'm good to go. So I just return without actually providing, right, an insert. And when I say an insert, I also mean like create a new node, right? So in these 3 cases, you're going to say, right, new BST node, right? In the fourth case, you're never going to say new because you're not creating anymore. Does that make sense? So those are my cases for insertion. All right, and we're going to go through them one more time. All right, with some sweet animation on the widescreen today. All right, brace yourselves. Okay, so the root is null, right? Our first case is the root is null. If the root is null, we just add the value there, right? So we just basically take, right, 5 and put it in there, right? if the root is null, remember the root's a pointer. If that pointer is null, we're going to point it to a new BST node. Right? In this case, that BST node has the value of what? 5. If it's new, right? So if it's null. Right, now if I enter the value 3, I start at the root, right? And I go through my cases. Is the root null? No. Is 3 smaller than the root's value? Yes. So which way do I go? Go to the left, right? And if that's null, I do an insert. Right? 8 comes in. Is the root null? No. Is the value smaller than the root's value?
No.
No. Is the value larger than the root's value?
Yes.
Yes. So which way do I go?
Right.
I go right.
So in this algorithm, you would be assigning the right child to the value of 8.
Right. Okay. So we're gonna get there.
Okay.
Right. Am I assigning left child? Am I gonna assign right child? We're gonna work through this algorithm and make it recursive, and then I don't have to know which child it is. Or if I want to insert 5, right? Right, value's equal, so I don't insert. You don't really create it. You don't want to create it. It just doesn't make sense. Right, and then 4. Right, is the root null? No. Is the value smaller than the root? Yes. So which way do I go?
Left.
Left. And then I run all the cases again. Okay, because there's a node there, I run my cases. Is the root null?
No.
No. And when I say root, okay, everyone get on here. So really, it's not root, it's subroot. Okay, remember, because a tree is made up of subtrees. So this is my tree, this is my root arrow, but this also is a tree, and this is its root arrow. Does that make sense? That's key for how we're going to write our algorithms. I have a tree with a root arrow, but I have a subtree with a subroot arrow. I also have another subtree with a what? Subroot arrow. And if you want to get technical, these both have pointers pointing to where? Null. And each of those nulls is its own subtree with its own subroot arrow. Remember, because when the tree is empty, right, we just have a root arrow that points to null. Right? And the recursive definition said, right, a tree is empty or. Remember that? A tree is empty or. So a null tree is a tree. Right? So nulls are trees as well. Right? So this tree, right, has what? 1 subtree, 2 subtrees, 3, 4, 5, 6. Right? There's 6 subtrees and a 3-node tree. Is that crazy? A little bit? There's a lot of subtrees. Right? So we go this way and then we do all the checks again. We said go left. So we do the same checks. Is the subroot null? No. Is this value smaller than that value?
Nope.
No. Is this value larger than that value?
Yes.
Yes. So then I go which way?
To the right.
To the right, and I run all the checks again. Is the subroot null? Yes.
Mm-hmm.
And if that's the case, that's your insert. Okay. So you only run an insert when the subtree or the original tree is null. That's where you do your insert, because that's when you're at the end and ready to do an insert. So now we put it in there. So when do we know to stop? When what?
When it points to null.
When it points to null, right? When the left or right subtree is null. So it's when that subroot, or I'm going to say this a lot today, that subroot pointer is null. So there's a pattern, right? We run the algorithm on the root. Either it's empty, so we do an insert, or it's smaller and we go left and we run the same algorithm on the left subtree, or we go right and we run the same algorithm on the right subtree, or it's equal and I do what?
Nothing.
Okay. When I say run the algorithm on the left subtree, or I say run the algorithm on the right subtree, what do I mean?
Running the function again.
Call the function again, but this time you're going to pass in either the left child pointer or the what? Right child pointer.
So this algorithm shouldn't be more than like 10 lines, right?
Correct. And today, to know if you're doing it right or wrong, if you write a loop, you're doing it wrong. Okay? None of your algorithms today require a loop. Even though you're like, oh, I'm here, but then I have to be here, and then I have to be here, right? Seems like a loop. But we do the loop via what? Recursion, right? By making function calls go on the stack. So let's talk about my insert function. My insert function needs two variables. What would those variables be? Anyone know?
Be the value.
Okay, the value to insert?
Yeah.
Okay.
And a pointer, right?
And a pointer. And what does the pointer point to?
The root.
The root. Although today I'm going to try to call it the what? The subroot. Because it will be the root of the tree, but then it'll be the root of each subtree. And so to not confuse us, right? Because we have root and we have root underscore, right? We'll call it subroot. So it's a little bit different. So then we have BST node, right? Star, right? Subroot. That's terribly lined up. Huh? Let's get better indentation. Right? So this insert function says, here's a value to insert, here's a pointer to a tree, right? Can you run the algorithm? The algorithm says, what's step one? If it's what?
No.
Right? So if the subroot is null, right? We found the location insert. Does that make sense? When the root / subroot is null, I found the location insert, right? I've traversed the tree to where I need to be. I can now do my insert. How do I do my insert?
Would you just set the subroot equal to the value?
Well,
Or the
I
original
can't,
root?
right? If the subroot is null, I can't determine left or right. There's no value there.
Wouldn't you just...
Right? I'm in the case where subroot, right, points to null. That's my tree.
So subroot equals new.
Right?
That's on the ESD.
Subroot equals new what?
ESD.
BST node.
BST node. Right? I think it has an overloaded operator. I don't remember.
So,
Right? To pass in the value. It's not overloaded. You should overload it to make it easier on yourself. Right? So the subroot equals a new BST node with that value. And then if we look at our private data and our BS tree, we also have another variable called what?
Size.
Size, and what's the size to?
Increment.
There's one crucial thing that I did not do in my algorithm. This star BST node needs to be by reference. Anyone know why it has to be by reference?
What is it referencing if it's being created right there?
What? Okay, so this is the memory address of what? Of the subroot? So, we're going to start in main, right? Are we good with that? And then in main, we're going to call insert. Are we good with that? And I'm going to pass in some value. So I'm going to insert 5. And the first time, what I really want to pass in is root. Does that make sense? To start it, right? Where am I always going to start my algorithms? At root. And then that one's going to call, right? And it's not where it's supposed to be. It's going to call insert. Right? It's going to call 5. And now it's going to be, right, roots, right, left. Right? I'm trying to do this little, right? It went left. And now I found where it needed insert, right? Because the root left was null. So it does its insert. So it says subroot equals what? New BST node. If I don't have an ampersand, it's not by reference, it's by value. Okay, and so we'll update the copy of the pointer, but it won't update the original pointer. What do I mean by that? Here we go. Well, kind of. Okay, so there's my tree. Everyone good? I have one value. I want to insert 5. Okay. When I call the algorithm, if it's by value, I get a copy, because it's by value, right? I get a copy, and that points to where? To the root, because I passed in root, right? And here was the parameter for that subroot. Everyone tracking so far? Right? Then, right? 7, right, was not where I wanted to go, so which way did I go? I went left. And so I get a second, right, instance of my insert function, right, because it's pushed onto the stack. I get a second instance, and subroot points to there. Everyone good so far? Okay, that's where I want to insert. Everyone agree? So I create, right, subroot equals what? New BST node and the value. So I create a new BST node, right, and I point this arrow to that, right? Give the value 5, its children are null. Everyone good with that? Okay? So I made it as far down the stack as I'm supposed to be, right? I did my insert, so my recursion ends. So this function pops off the stack. What do I lose? I lose the copy.
Oh.
Right? And then this pops off the stack. What do I lose? The copy. Okay? Notice, what did I not erase on my tree? The null. Because I didn't affect this arrow, I affected the what? The copy. Okay? That's by value, because by value gives you a copy. Now, I changed it to be by reference. That means when I call this arrow is subroot, right? Because by reference says I'm not actually the variable, right? The thing that called me is the variable. So the first time when I call root underscore, right? Subroot and root underscore are the exact same thing, right? Because it's by reference. When I call it again, then what? That arrow is the same thing, right? Because it's by what?
Reference.
By reference. Which means in this case, if I say subroot equals the new node, then the subroot arrow is going to be the new node. Function ends, this pops off. Function ends, this pops off. And it's a tree, right? It's not a weird tree with memory. Right? Right? Yeah, I don't know. Does that make sense a little bit? So the ampersand is super important when you're changing the structure of the tree. Okay? And you'll see in the lab today that inserts by reference and deletes by reference, traversal, right, get to every node, that doesn't need to be by reference because, right, we're not changing the tree, right? We don't want to change it. Okay, so it's just the other algorithms that need the ampersand. All right, first case, it was null. That's what I do in insert. Does that make sense? Now, second case, what do we say? If what?
If it's smaller.
Right? Else, if the value is smaller than what?
Root underscore arrow, like,
Okay.
value?
So I could do root underscore, but remember, these algorithms are recursive. I'm going to call it again, so I don't want to get stuck at root underscore.
Oh, yeah.
Remember, when I called the function, I passed in root underscore. So what do I want to work with? Say it louder. I want to work with subroot, right?
Yeah, because that comes back into the function, right?
Anyone know the name of our accessor? I want to write it on the board so you get it. I don't remember what it is. Is it get contents? Is it contents paren? Anyone know what it is?
Get content.
Get contents. You guys wrote it, so.
Capital G, capital C.
Is that what it is? Arrow get contents. Remember, it's private in the node. Oh, I'm gonna. If the value to insert is smaller than the subroot's contents, right, the thing you're pointing at, then which way do you need to go? Left. All right, so you want to go left. How do we go left? Okay, so get left child gets us the left arrow. Okay, so I call insert again. Right, insert takes into the first thing. What does it take in?
The value.
The value, is it the same value that I'm still adding? So what do I pass in? Same value. Right, nothing's changed. And what?
Ah. Success.
Success, right? You're at the top of the tree, your value's smaller, you need to call insert on the left subtree. Right? Does that make sense? I'll insert on the left subtree. Let it deal with the subtree and figure out where in the subtree it's supposed to insert. You just know, hey, I'm here. Nope, I'm not supposed to insert here. Go do it again over here, right? Or go do it again on the right side. Which means that your next else if is basically the same thing, right? Else if what? Value is greater than
The contents.
right, subroot. Get contents. Then we do what?
Insert value, right child.
So this time we go get right child. So don't copy and paste.
What would happen if we just said get the left child again? Would it just keep going?
It would, I mean, we go back and I do it again. Oh, it's not null. Is it small? Is it larger? Right? So eventually it would insert it in the wrong spot.
Yeah.
You need to return on your sizing point?
In this one?
Yeah.
Well, no, because it's in this case, right? So it's not going to hit this case or this case. And then there's my.
Oh, I see. The else if prevents it. The else from.
Do I need an else in the way that I've written this algorithm?
Yeah.
The else is what? Don't insert. If I make it void, I don't need an else, right? Because it says don't insert. Well, it's not null, so I'm not creating a new one. It's not smaller, so I'm not going left. It's not larger, so I'm not going right. So I'm just done. What?
Equal.
No, because if it's not smaller and it's not larger, it must be equal. So I could do an else, but the else's don't do anything. So I don't need an else to say don't do anything.
And
It could be in your lab that you're supposed to return a Boolean. I don't really remember. Supposed to return a Boolean, then you're going to have to return true or false. Right? Did it insert or did it not? So this isn't perfect for what you have to write today. It's pretty fast.
So after that last else if we just return a false. If it was a return rule.
Mm-hmm. So if this was Boolean, on the insert you would return what?
True.
True. And on the else you would return?
False.
What do you return in these ones? Because remember, every case needs a return.
Won't they just run the function again?
Well, they run the function again. Remember, but if this insert function returns true, then this line of code becomes what? True, but then you would just end the function, so you actually wouldn't return anything, right? You get that function returning non-void, right?
So you return right after that call.
So you would what? No, you'd actually.
Oh. Okay.
Because you don't know what, right? You're basically saying, you came to me, I'm not where you're supposed to insert. You're supposed to insert in the what? The left tree. But in that left tree, you don't know if it doesn't exist or it does exist. So you don't know if this function is going to return true or false. So you just return whatever value comes back. If that function returns true, great. It was true. If that function returns false, great. Right? False. It already exists. So you have to be careful about this.
So you return the function insert.
Huh?
You're returning the whole function.
Return the whole function.
Well, the function returns like a Boolean, and then you're returning whatever that returns.
Right. Remember, a function call becomes the value that is returned, right? So this insert function becomes a value. I just return that value.
Is it because you're trying to catch it when it comes off the stack?
Mm-hmm.
Yeah.
Right. So if I do 5 inserts, right? And this one says false, that's what's returned, right? That's great. This function knew that it was false. This function does not know that it was false, right? Unless in this function I return that value again, right? And I return it again. So I need to propagate it up the stack. The only way to propagate things back up the stack is to return. The only way to link two stacks together is by reference, right? Which we did, right? This, right, function has access to the variables in this function by reference, right? And this function has access to the variables in this function by what? Right?
Based on things that don't exist yet.
It's so fun. Then we'll have like 10 lines of code. 1, 2, 3, 4, 5, 6, 7. You call, is that a line of code? 8?
Yeah.
9, 10. Boom, done. 10 lines of code. Do we write a loop? No loop. We don't need a loop. Right? Everything's working just fine. Do you want to see if it works? Sure, why not?
Well, would you need the size to increment like somewhere in those else ifs?
Ooh, great question. Do we need size to increment in either of these else ifs? No. What happens if I incremented size in them?
You'd be incrementing size without actually adding.
Right. I'd be incrementing size without adding. This is the only time I add.
Okay.
If I did this and I had to go like 8 levels down to insert, I would increase size by 8. But I'm only adding one thing. So I think drawing it out will help us. So at the very beginning, the root is what?
No.
No. Everyone good with that? So what value do you want to insert?
10.
10. Okay. So we're going to insert 10. Right? We're going to call that function value is what? 10. And when I start, I always pass in the root. And so in this case, that is my subroot. Are we good with that? And then we run. Is the subroot null?
Yes.
Yes. So what do I do? Subroot equals what?
A new node.
New BST node. Right? With the value, which was 10, right? And we made the constructor, right? Point new nodes left and right children to null, right? That's in the constructor. So we don't have to do that. It's done automatically for us. All right? And then what happens to size?
Goes up by 1.
Goes up by 1. And then the function is, right? So we're done? Agreed?
Yeah.
Pops off the stack. I didn't draw the stack, but right? That popped on the stack, then it popped off the stack. All right? Here, this is how we'll show popping off, right? Pop off the stack. Now what value you want to insert?
7.
7. Okay? So, call my insert function. We always start at where? Root underscore, right? I'm going to pass in root underscore to it. So this becomes, right, subroot. We're trying to insert 7. Is the subroot null? No, right? So this is false. So we go to the next condition. Is the value that we're inserting 7 less than the subroot's contents? And the subroot's contents is 10. So is 7 less than 10?
Yes.
Yes. So I call insert. I'm still going to insert 10. But now I pass in the left child arrow into my function.
Which is null.
Right? So subroot becomes this arrow. Does that make sense? Right? This arrow gets passed into subroot, so subroot and this arrow of the left child of where I'm at becomes subroot, and it's by reference. So this becomes what?
Subroot.
Subroot. Does that make sense? I'm in, right? I recursed. Right? I went one level deeper into my recursion because I called the same function. Right? I'm in the same function, but I'm at a different location, right? Basically, I'm at a different subtree in my tree. Does that make sense? Questions on that? Okay, so if I'm back in my function, I have to start at the beginning. Is the subroot null?
Yes.
Yes. So my subroot equals a new BST node. Right, so my subroot equals a new BST node with that value, which was 7, and its left child always starts at null, and its right child always starts at null, right, by the constructor.
Wait, so when you pass in the value of 10 in that else if, right, and it comes back into the insert function, what happened to 7?
Which time?
When you go into the first else if and you have to pass in the value of 10 again?
No, we have not 10.
Oh.
Value's still 7, right?
Oh.
7's less than 10.
Oh.
So we insert 7 on the left side.
Okay.
All right, okay. We did that, which means we don't do this else if, which means we don't do this else if, which means the function what? Ends. When the function ends, this pops off the stack. Okay? That pops off the stack, I'm back to this. I was right here. Okay? When that happened. Because I inserted on the what? The left subtree. Right? Well, I'm in an else if, which means I don't run the else. Which means I'm at the end of my function, which means what happens? Pops off the stack. Right? Notice root's fine. Right? Size got incremented again. Is 7 where it's supposed to be?
Yes.
Okay, we're going to do one more. We're going to insert 8. And then choose it this time. Right, so we're going to insert 8. So I call the insert function. The value is 8. The subroot starts out at where? Root. All right, so this is my subroot. Is the subroot null?
No.
No. Is the value 8 smaller than the subroot's contents? 10.
Yes.
Yes. So I'm in here, right? I'm going to insert 8 in the left subtree. Okay? I'm going to pass in, right, this arrow, because that's currently the subroot's left child, this arrow, think sometimes students think that it's this node. It's the arrow to the node, right? So it's very similar, but really it's that arrow. I'm going to pass that arrow into my function. So I'm calling the function again, value still 8, and the BST node star ampersand subroot is this arrow right here, right? I'm recursing down the tree, right? This is my whole tree. Currently, this is my subtree, right? 7 with 2 null nodes. Does that make sense? So when I call a function, I always have to start at what? The top. Is the subroot null?
No.
No. Is the value 8 smaller than the subroot's content, 7? No. I go to my else if, next else if. Is the value 8 bigger than the subroot's contents?
Yes.
Yes. So I call the insert function, I pass in the value, which was 8, and I pass in the subroot's what? Get right child. So I'm passing in the arrow to the right subtree, which is this arrow. Agreed? Well, when I call a function, I have to go back to the what?
To top.
To the top of the function. Is the subroot null?
Yes.
It is null. So now I go into that, right? Subroot equals new BST node. So subroot equals a new BST node, right? Whose value is what?
8.
8. Size goes up, right? Size goes up, right? This if ends, that else if, and that else if were connected to that if, so we skip both of those. What happens here?
Ends.
Ends. So this pops off the stack. And now I'm back, right, with this subtree. Well, with that subtree, remember I was right here, right? So then closing curly, what happens?
Pops off the stack.
Pops off the stack, okay? When I called that one, I was actually here, right? I ran the if, so I don't run the else. Curly brace ends, what happens?
Pops off.
Pops off the stack. Is it a binary search tree?
Yes.
Yeah. And I know I never went right here, but remember I went left, and I did go right as well. Right? If I insert 10, right, this becomes a subroot, right? Is the subroot null?
No.
No. Is 10 smaller than 10?
No.
Is 10 bigger than 10?
No.
So then the function ends and, right, it just pops off. Now, it could be 8, right? So, well, it's not null. It is smaller, so it goes this way. It's not null. It's not smaller. It is larger, so it what? It goes this way. It's not null. It's not smaller. It's not larger. So what does it do? Pops off the stack. Pops off the stack. Pops off the stack. Right? So it's going to work not just at the top of your tree, but it's going to work once you get down into a bigger tree.
Isn't that the only downside to a tree? Is it uses the memory to like check
You know what?
all the way down the
That's
tree?
the downside of all the recursion. Is the overhead of the node.
So if you had like a huge tree and the value that
It's not going to be as
matched,
efficient.
yeah.
But it's elegant, right? And you care about that because 10 lines of code.
Writing period later is really hard.
Yeah, right? Not so fun. Insert's not too bad. Some of the other ones get kind of crazy. Does it make sense? I know I spent a lot of time on insert because I wanted us to get used to how does this recursion thing work in my tree, right? It works because every spot you go into a tree is a subtree of your original tree. Even the nulls are subtrees of your original tree. And so you can apply the same algorithm to every spot in your tree, which is super cool. You see the pattern? You see the code? Any questions on the code? Besides, you might not be able to read it. Remember, this isn't, right, necessarily compilable. Compilable? I don't know how to say that. Right, it won't compile, but it's close to what I'm having you write today. Look, I wrote some of your class, wrote some of your functions. Must be close to Christmas. Yeah, right, here you go. All right, we did that. Yay, yay, okay. Yay, we did that. Yay. This is the pseudocode, but guess what? You don't need the pseudocode today, because I give you the code code. That's so nice. And it works. Yay. Okay, clear. So to clear a tree means to get rid of every node in the tree, just like to clear a linked list is to get rid of every node in the tree. Right? So this says to clear the tree, we need to do what?
Delete everything.
We need to delete everything, which means we have to go to where?
Bottom of the tree?
Right, all the way to the bottom and all the way back up, right? We have to go to every node to delete it. Unless you like memory leaks. And then you just set root to null, right? Tree's empty, right? Ready to do the next thing. But we don't like that.
That would be
We want to delete every node
That's a
that was
huge leak.
right? So we need to traverse the tree. Remember, we have 3 ways of traversal. Pre-order, in order, and
Post order.
post order. And last class we talked a lot about those, and we said for deletion we'd probably use what?
In order.
Which one?
In order?
So in order says what?
It goes.
Go left, visit, and then what? Go right. Remember, for us, for deletion, visit means delete. Right? So if I delete, can I go right? No. So in order is not going to work. Post order says go left, then go right, and then delete. So I'm going to go left, which basically says delete the left subtree. And then we're going to say go right, which basically means delete the right subtree. And if I got rid of all my children on the left side, that sounds so bad, and all the children on the right side, right, if I got rid of all those, then what can I do? I can delete right where I'm at. So post order is the way I want to go. Because I want to go left, then I want to go right, and then I want to delete. Now remember when I say go left and go right, because we're doing recursion, that means call the function, right? This is basically go left, right? Call the function on the what? Left subtree. If I say go right, it's call the function on the right subtree. Okay? So when we delete left subtree, we delete right subtree, and then I actually use the lowercase word delete to actually delete the node down there. So long as what? The root is not null. Because if the root is null, can you delete it? What'll happen? Sigfall. We love sigfall. Right, yay, we said that. No, doesn't work. No, doesn't work. Does that one work?
Yep.
Yeah. I was going to take you through all this of like, oh, look, pre-order, right? Pre-order says, what do we delete first? Right? Remember, pre-order says visit first, right? So what do we delete first?
Okay, root.
8. And then it says go left and go right. Is that going to work?
No.
No. In order says, go which way first? Left. So, yay, 8's still there. Go what? Left. Yay, 1's still there. What do we do? Can't go left, so I delete. Things are looking good, right? It says go right. That's probably going to crash my program, but let's just say it doesn't. I come back up to 3, and it says to do what? I've gone left, so now I
Visit.
I visit, right? And in order, I visit. So what do? I delete 3, and what happened to all these guys?
They're still there.
Hanging out. Woo! Still alive in our program.
Under the radar.
Right? So in order doesn't work. Right? Post order says we go which way first?
Left.
Left, then
Right.
right, then delete. So we go at 8, go left. At 3, go left. Can't go left, can't go right, so we delete. We come back to 3, gone left, so now I go
Right.
right, then I go left, can't go left, can't go right, so I delete. I've gone left, so I go
Right.
right, can't go left, can't go right, delete. Already gone left, already gone right, so I
Delete.
delete. Already gone left, already gone right, so I
Delete.
only have gone left, so I have to go
Right.
right. You don't even keep going, right? Right? Post order says, remember, post order says when you visit, it's the last time you're going to see that node. Pre-order says it's the first of 3 times that you're going to visit. Right? In order says it's the second of 3 times you're going to visit, and post order says it's the 3rd time of 3 times you're going to visit. Remember we did the family circus and remember the dashed lines all the way around? Right? Pre-order says you visit here. In order says you visit here. And post order says you visit where? Yeah, right? And then you're done. Right? So post order is the way that you want to do it. So post order. Right? Clear the left child, clear the right child, and then clear the root. Right? And that's so long as what?
Because the root is not
So
null.
long as it's not null, right? Apparently I'm feeling really cheerful today. Right? Clear something subroot. Okay? The algorithm says so long as, right, the root is not what? Null. And so we don't mean, okay, in all these algorithms, I never mean root underscore. I really mean
The subroot.
subroot. Because the algorithm applies to my whole tree, but also applies to each individual subtree inside of the whole tree. So it's not root underscore, it's subroot. So if the subroot does not equal what?
No.
No. Okay, then we're going to do something. Right, and we'll do that. And what does the algorithm say to do? It says clear the what?
The left child.
Right, so I call clear. Right, and I call subroot what?
Left child.
Yeah, left child. Right. If that doesn't blow your mind, I don't know what does. I'm writing the clear algorithm, and in the clear algorithm, basically the first thing I do is say, I don't want to clear, go to the left subtree and clear over there.
Oh.
Right? I mean, that's what it's saying so far, right? It says, so long as I'm not at a null location, I don't want to do any work right now, go clear the left subtree. Right? This is called delegation. Right? I think someone else do it. This is why you have kids. You go do this. Right? I don't want to do it. Right? After we clear the left child, what do?
Clear the right child.
We clear the right child. Subroot arrow what? Get right child. Right?
So clear would have to be overloaded?
No.
Because
Right? It takes in one pointer.
Oh.
There's a pointer, there's a pointer.
Oh.
So it's not overloaded. Okay. Once again, in recursion, you have to trust that what you're saying the function is going to do will actually do it. Okay? So even though I haven't written the code to do it, the clear algorithm is supposed to delete all nodes in a tree. Agreed? So if I call the clear algorithm on the left subtree, it should delete all the nodes in the left subtree. If I call the clear algorithm on the right subtree, it should delete all the nodes on the right subtree. Does that make sense? Even if you don't think my code does that, we have to assume that it will. There's a lot of faith in recursion. Just like when you delegate to other people, you have to have faith that they're going to do what they said they're supposed to do. Agreed? Now, if I got rid of all the children on the left, right, and all the children on the right, what can I do? I delete the node that I'm at. I don't need an if statement, right? I said the left subtree's gone. I said the right subtree's gone, guaranteed, right? Because those clear algorithms, in good faith, will do that. So then what do I do in this algorithm?
Clear the root, right?
Okay, I clear the root. I'm at the root, so I don't want to call clear. I'm where I want to delete.
Oh, set the root equal to null, right?
Okay, but before I set it to null, right, that will just set the pointer null. What do I need to do? I want to delete the subroot. Then I can set subroot to what?
No.
Null. Which actually doesn't matter for the most part, because if you think about it, if I delete 8 and I set this to null, once I delete 7, that arrow's gone, right? But when I get all the way to the top where root underscore is, when I delete 10, I need root underscore to be what?
No.
No, because the tree is empty now. So I want to make sure that's set to null. And then you should do what to size?
Decrement it.
Did you say increment?
I said decrement.
Good. Yeah. Look, it's not even 10 lines of code, guys. Do you want to see if it works? Yeah, go left first.
Go left again.
Yeah. So it goes a little bit farther than maybe you want it to go, because you're going to get extra function calls for the nulls. But that's fine. Right? So I start here at root, right? Subroot being root. Everyone good with that? Subroot is that, right? Then I say what? If the subroot isn't null, is the subroot null?
No.
No. So that's true. So I go here. I say clear on the what?
Left child.
Subroot get left child. So I'm here. Everyone good? Right? And that one, is the subroot null? No. So I call clear on the left child. Woo! So I'm here. Right? Remember, a null tree is still a subtree. This is I love this function call, right? I called it. Is the subroot null? Yes. Function ends, right? Pop it off the stack.
But it doesn't delete it, does it?
Well, there's nothing to delete. That's a null. You can't delete a null. What'll happen?
Oh,
Crash my program. That's it, right? So it takes the extra step of going down. And yeah, you could write an if statement and that would save it. You can do that if you want, but who cares? So I'm back up to here. In this function call, I called clear on the what?
the left,
The left subtree. So now it's a call clear on the
right.
right subtree. So I'm here, right? And the clear algorithm says if the subroot's not null, which it's not, I call clear on the what?
Left.
Left. So I come down here. Is the subroot null? Yeah. So now I pop back up. Woo! But I don't even have time to drive. So I'm here. I just called clear on the left subtree, so now I call clear on the
Right.
right subtree. So I'm where?
Right there.
Right there. Is the subroot null?
Yep.
Yeah. I'm like Vanna White. Right? Back and forth, back and forth. So I traversed the left subtree of 8, and I traversed the right subtree of 8, and I cleared everything. Agreed? So I've done this, and I've done that. So now I'm going to what?
Delete the subroot.
Delete the subroot. When I call delete on the pointer, it deletes what the pointer is
Pointing to
pointing to. So
group 8.
8 goes away. Are we good with that? Then it says what?
Set it to null.
Set it to null. And size goes down. Okay, then that pops off the stack, right? Because the function's over, right? So this pops off the stack. I'm at 7. 7, I've already gone left, and I've already gone what?
Right.
Right? So now what can I do?
Delete.
Delete it. So goodbye. Remember I said that to null? I said it's not really a big deal for that time. Right? Sets to null, or sorry, deletes, set it to what? To null. Size decrements, closing curly. So subroot does what? Pops off the stack. I'm back to basically my first function call, right? Remember I like added all these function calls to the stack, and now I've actually popped all the way back to where I was originally. But in that function call, remember I called clear on the left child?
Mm-hmm.
So now I need to call clear on the what?
Right.
The right child. Right? So that's subroot. Come back into my function again. Is the subroot null?
Yes.
Yes, so we skip the if. Closing curly, what happens to the subroot?
Pops off.
Pops off the stack. I'm back to my original function call again, right? For the what? The third time, remember? Right? We visit a node 3 times via the stack and recursion. When I push it on, when I eventually come back to it, right? And then when I pop it off, right? Those are the 3, right? I've done clear on the left tree. I've done clear on the right tree. So now what can I do? Delete the subroot. Remember, this is all by reference, so subroot and root are the same. Right?
Mm-hmm.
Yeah. Right? I delete the subroot. Subroots get set to what?
Null.
Null. Size goes down. Function ends. Pops off the stack. At the very end, when you clear your tree, root underscore should be what?
0 or no.
No, right? Because I removed all the nodes in the tree. And the other thing that should happen is that all the nodes in your tree should be what? Gone. Are all the nodes in my tree gone?
Mm-hmm.
Yeah. Did you have the faith? I don't know if you did or not, but right? The algorithm says remove all the left subtree, remove the right subtree. When those 2 things are gone, you can remove your node. If you apply that recursively to every subtree in your tree, they'll remove all your nodes for you. If that's not cool, I don't know, right? What cool is, guys?
Oh, just
You're like, you don't know what cool is. That's what we said.
I guess most of the time is taken getting to the bottom of the tree, and then it just speeds up.
Yeah, right. Yeah, I could have put the function calls, right? We could have looked at the function calls on the stack.
What happens if you switch get right and get left child? Is
So
that
if it's like go right, go left, as opposed to go left, go right, nothing.
it's the same
They'll
thing?
just get rid of the right subtree before the left subtree. The key is that the delete is at the end. But then you want to write it like I told you to write it. But it'll still work just fine. Doesn't matter, right? Now, if you try to do like other algorithms, right? If you try to output and you switch that, then you're gonna get a totally different output, right? It's gonna output the whole right subtree before the whole left subtree. All right. I went backwards. Let's go forwards. Questions on clear? Right? There's the thing. So long as the root is not null, right? This is your pseudocode. So long as the root is not null, call the algorithm with left child as the root. Call the algorithm with what? Right child as the root, then delete the current root. Right, so that's null. That makes sense. Is that gonna work for us?
Hopefully.
Hopefully. Right? I'm taking time. My lecture's going into your lab time, but that's because I'm running your lab during lecture. So right? I'm assuming you're okay with that, right? If you're not, then I could just stop and say, okay, there's the rest of the slides. Good luck. All right.
It has to be used for post order in order.
We are.
So we learned it, but not going to
But
use
we use, like, remember, we did the HTML structure of a web document, right? That used pre-order because it was the HTML element and then it was the head element. So there are places you will use it, but for a binary search tree, you're not going to use it. It's just going to look ugly. Should I give you the hint now that on your paper test, because you guys love the paper portion of this, on the paper test, I'm going to say, like, I'm going to give you a tree like this. I'm going to say, okay, output it in pre-order and order and post-order.
Easy.
Not write the algorithm, but just can you output it?
Yeah.
It's easy. Why is it easy?
You just draw an arrow.
Draw the dashes. You don't have to write, they don't have to be dashes. Just draw the, right? Literally draw a line, right, around your tree.
And then just put dots on it.
And then just put dots on it, right? You don't even need the dots, right? Oh, this is the first time I saw it. Great, right? If it's on the left side, the line's on the left side, I'm outputting it. The line's on the middle, that's in order, I'm outputting it. If you don't get in order correctly, right? I might just give you a 0 for your whole file. Okay? It's going to be a binary search tree, and it's going to say output it in order. Please output it in order. Like
So what if someone puts it randomly?
Right. It's not going to be random, so it's going to be in order. And then post order, right? On the right side.
There's something wrong if someone even put that in order.
That's right. Go left, go right, visit. That's post order. Okay. Let's talk about in order right now, right? If I want to output my tree in order, right? My slides say what traversal method am I going to do? Is it going to be pre-order, in order, or post order? Come on, right? In order says we go left, right? So go down the left subtree, then we visit, and then we go down the right subtree. Okay, this should make sense. A binary search tree says everything to the left is what? Smaller. Everything to the right is larger. So I want to output something in order. I want to put all the smaller values out first. Then I want to output my value. And then I want to output all the larger values. Right? Does that make sense why it works in order? Output all the values in the left subtree. Output me because I'm larger than all those values. And then output all the values in the right subtree, which are all larger than me. If you do that recursively in every subtree, then you should get everything in order. Agreed?
So it starts at the first null that finds one left.
Then that's where I'll stop.
Well, I mean, that's the first one it'll output.
Yeah. When it's left child is gone. Right? So, right? That algorithm is going to look a lot like this algorithm, right? Where you go left, meaning you call the function left, right? Then you output yourself, and then you output left. The only difference is that because our nodes are integers, and I want you to make a string, you're going to have to use what? String. So it's going to look a little bit different than that, right? Because you're going to have to slap things into a string to do stuff. But you can just slap into the string the left, right? Call the function with the left subtree, then string your contents, and then string the right subtree. So it's not that much harder, but it's a little bit. Look, I'm not going to do anything with that. Good luck. The best thing that I can tell you for how we do the string is that when we did the recursion lab, right, we did output the array forwards and the array backwards, right, where we had to use a string. Right, and then that string, right, for us, we need to slap in order on the left subtree, then we just need to say the contents of where I'm at, and then we're going to slap into the string in order of the right side. Space separated, I think, or comma separated.
You change the order type depending on where the input and the strength is, right? And
Depends on where you throw it, right? So, right here, they were like distinct function calls, left, right, back, right? Now it'll be throw into the stream left, throw into the stream where I am, throw into the stream right, and then return SS status. Does that make sense a little bit? Maybe? You guys ready for me to grade assignment 4 on Friday? Yeah? Some of you are, some of you are not. The ones at home are not, right? You guys are okay. Assignment 5, right, is still due in 2 weeks. Right? Assignment 5 is this, right? But it's templated, so instead of it only working for integers, it'll work for integers and strings and doubles and characters and blah, blah, blah. So you can kind of work on both in tandem, right? You can get the lab working, and then you can kind of add that functionality to your assignment, right? That way, right, when you're super stressed out the last week of school, you don't actually have to do anything on this. It's kind of been nice probably for you that grading's been lax and things are, right, not due when they're supposed to be due. But the problem is that when the semester ends, everything's due. So we've only been lax for so long, but things are now catching up, right? Because you can't do assignment 5. I'm not going to grade it on Christmas. It's not going to be due on Christmas. I can make things due on Thanksgiving, but I'm not going to make things due on Christmas. Right? So our last assignment is due, right? The last day of class.
I can understand why Christmas could be the Grinch.
Yeah, that's good. My wife's the Grinch. She'd allow me to say that. She's the Grinch. I want to enjoy Christmas. So. And you want to enjoy Christmas by getting a good grade in the class, right? Maybe I'll post your grades like Christmas Eve. I'm gonna hide all your grades right now, and then I'm gonna post them on Christmas Eve. Yeah, exactly. Oh, really? What's up? Yeah.
I gave you great things, but like
Forever to put it online. So yeah, I will be grading assignments 2, 3, and 4 this week, and probably labs up to like 22 or something like that. So there's a lot being turned in, but you've already done all that, so we're not worried about it. There's only today lab 24. Is that true? 23.
24?
Today's 24. There's only 2 more labs after today, so 25 and 26. There's technically, I have a lab 27 that's written, but I just haven't updated it to you. Doesn't that sound great? Kind of shoots myself in the foot though, because I'm going to lecture about all that stuff, but then
Never see it again.
It's actually really nice. The last lecture would be like, hey, you know all the stuff that I made you do manually all semester long? Here's all the stuff that makes it actually, right? So here's an already written linked list. Here's already written dynamic arrays. Does that sound nice? Yeah. Believe it or not, you're not the first people to write linked lists and arrays and trees. So I know that might blow your mind, but yeah. So other people have written them and they work. Not to say that yours don't, but these for sure work. So. Any questions? Make sure you get Code Envy off of Code Envy and onto Red Hat OpenShift, I guess they call it. All right. Which basically just means that make sure that all your code, I mean the key is by Sunday you need to make sure all your code that you've written this semester is on GitHub. GitHub's not going down, you can pull it down to any environment. But you need to make sure that anything locally on CodeEnvy, right, has been backed up to GitHub. So that way you don't do it. Yeah, just commit. I would just, from the root, I would git add dot, because dot is everything. And then git commit and git push. Make sure you do all those things. You shouldn't have to add the class refill on your new one. I didn't put instructions for that because at this point I pushed everything in the semester, so there shouldn't be anything new to integrate. Probably not making money? I don't know. I mean,
They got bought out
by Red Hat, is that what happened?
Yeah.
So. Why they only gave us like 2 weeks notice before it's like, and we're closing for good. That I don't know.
It was a good idea, like, services, but I just think that, like, It's such a good idea, somebody else thought of it, and I was like, oh, let's sell it.
Yeah, I'm gonna work with this. The new, so we were on Eclipse Che 6, version 6. Red Hat has the new version, so Eclipse Che 7, which is a lot better actually. Just a little bit that I think. How about this? The editor is a lot better. You get syntax highlighted in your H file, and your whole last assignment is written in an H file. So to have syntax highlighted, I think would be really nice.
Drag things so we can.
You can actually drag things in the panes. Yeah, right? It's kind of weird, but it actually is like a normal, up to date kind of thing. Let's see if I can open up a file.
Oh, that's what I feel like.
I think it went to, did it go sleep?
I was still used to writing with the blue H file and editing, but when I wrote in
Something else?
the last test, I wrote in Notepad++ and didn't change it to C++, so it was just like text. I changed it at the end and then everything changed, and I was like, oh, shit.
Look, there's actually syntax highlighting.
I didn't know.
Okay.
Remove all.
Yeah, so you can move them.
Yeah, now I need to figure out how to get this. But I don't think it'll be that hard.
Alright, so the same thing is now,
So,
this looks more like.
Yeah, you don't need to do
This looks more like
it.
the first. This function, we're only removing, right? The only variable is find where you want to delete, or where you want to delete. But you only delete it once. That doesn't sound like it's all.
If we're not entity.
so if I want to.
So if you want to do
Closing out, I just keep going.
So basically, the difference between remove first and remove all is that in remove first, you loop, it stops, you delete. Right? And this, and remove all, you basically take all these conditions and you put them inside the
So
wall.
that's true, but
Yeah.
change them. In fact, it's important because when you're going down the list, because eventually you get to the middle of the word, you're not.
We have to put it over. So, same idea, we have like a,
That's why
iterator.
it's.
And you also need like a, you can use head as your.
Honestly, way more
Basically,
basically. So.
Let's say your list has two nodes.
Think of it like
This is the head node, right? So head is pointing to it, you need either to move head forward and have a different thing pointing to it, or it just depends on the
It's
word.
gonna be your.
Or your iterator can move forward. I like to do
So your
that.
first is gonna be your
I
stop.
take my iterator, I move it forward, then I go to head, then I catch head after my iterator. And then I keep doing that. If I do that onesie twosie, it'll delete and move forward, and you loop while the iterator is in.
You create like a current pointer. When you're not, ahead of the next one.
So,
If I'm trying to.
VL node, dot, iterator equals head.
So you just return to that.
So it works, and then while the iterator isn't null. So the iterator is null, that iterator goes forward. Right, how the iterator forward, the iterator, iterator,
Zero.
right, the next. Right, the iterator moves forward. It was, they were both pointing to the same thing, right? So we had head, we had iterator both pointing. Right, so there's that. I know it's double line. It's gonna work. Right, so we just said the iterator moved forward, so the iterator points here. So what do we do? We got,
Instead of having more return ball.
just goes away. Right?
Yes.
So, I mean, does that line make sense?
Same place, right?
Yeah.
And the reason then is the iterator null? Because it's not, right?
Increments.
So the iterator moves left.
Yeah. Well, it was as high as,
Yeah, exactly.
So you're looking at the first one and the last one.
Iterator is not null, so the iterator moves left. Or goes left. Right. We delete
So that'll be the return on.
Right. Head goes here.
So this is where, so the one thing you're missing in recursion, what do you do in recursion?
You just get two points. You can't do it with one,
So that's.
because if you delete where you're at, you can't.
So where you're calling. You're always gonna call recursion, it's somewhere. So, yeah, this is where you're calling.
You can, if you want to test it, and then obviously my unit test it.
So, and then you're
So
passing.
you could make your own, create the list, add a couple values. Make sure they're there.
That should be.
Yeah.
Okay, so like, I don't know if you heard me right or not. Anyway, minus.
I was gonna see it.
And then just, yeah. And then the logical proof here, so this is, so basically, you're looking at a string inside a string.
I'm gonna show you, I'll show you a couple things that I found so far. I mean, you're gonna find a lot of things too. So you can drag, right, files side by side. One thing I like, if you double click a file, it gets rid of all of your noise. You just have, right, what you want. I think it'll keep, let's see, if I add in the terminal, I think it'll keep the terminal back. Let's see, so I open the terminal. Come on, terminal. I think it'll stay if I don't. No, it goes away. So you don't get the terminal, but you get all the other ones.
Oh, that's what I'll do. We try to make a file lab 2324 and still give you that error saying, hey, we can't find, you know, BSC page.
Okay.
So I use it to delete it, and we edit it. Delete that. Oh no, we found it. So here.
So if you make your browser go full screen and you get rid of the noise, you actually get like a full screen editor. Which is kind of cool. Double click it, click it, and go back to this, but it's still full screen.
Where's your stock cases? It's either based on the stock cases around or index. Your start is greater than or equal to size. The reason it's equal to is because size is being incremented as it's passed in, so it's already.
So for the one, kind of like this upgrade backwards.
Correct, because, correct, I'm trying to how you pass it. Oh, right, okay. Well, basically the idea is. Yeah, because you're not there. So basically, it's if the string is empty already, you return an empty string.
This here is the
And then the idea is, so if it's empty,
That doesn't get out.
and then the second case, so if the string is empty, that's what they have to say. If it's not empty, you
Basically that in order line.
you're incrementing start, is the spot. Or you're going to be, you're not going to be, you're going to be incrementing start, mine's called. Yours is when we start plus one. So basically, this is changing, but this is not.
You should be
So as soon as
close
this
to what you
becomes
want.
the same as that, or bigger. I don't know why the bigger.
No, you should write it in your system.
Whatever it's rate, you're using it starts.
Okay, so that's because, okay, so you're gonna have two versions of insert, two versions of
You need to modify your
and
index.
two versions of
And the
insert.
size needs to be passed.
And that's because we want the user to call my function and pass it, but we don't want the node to know about it. So they just should call one in order. So our public in order function just calls our private in order function and passes it.
Yeah.
So you have, so if we look at this, so here, okay, so let's look at the insert function. So this insert function just takes an int, right? But then we're gonna write another insert function that takes in an int and a root. So in the public one, we're gonna call this one and pass it. So you're gonna have two, basically you're gonna have a function that starts the recursion, and then you're gonna have a function that is the recursive function. So this is like the private one's the big one, that's the recursion one. This one's just like calling. There's not much, there's like one line. Well, you declare both of them in the H file and then you write the definitions in C. So the guts are always going to be the CPP. So these are the private ones. But those private ones are referencing these, right?
And then you can write the private and the community members with and the private sections of the
With those, yeah.
Okay.
That's what it is, you start and you're modifying it. And then you just, then you pass an unmodified class. Yeah, I know. When do you use to correct those methods?
Every time I was class.
Yeah, exactly.
My experience, it didn't matter what you have to really get to see it. Go and what is it?
It's the same value, but it's garbage. I mean, just, size,
It may not correctly implement or reject, it may be not correctly implement or recommend. Actually, you don't do that anyway because. Oh. It's not size, it's, stars.
With A, B, and C.
But have you written the backwards one?
No, I'm just, making sure that that's all the text and
Whatever was
text.
copy pasted, that's all you have to change that plus one.
Thank you. I was looking at, like articles, trying to figure out the version word.
You have to just keep saying you have to update. That's just to start up with being based. You're not worried about how what you're gonna do. You're based, you're just happy. And then you figure out how you're gonna do it. Then you figure out.
Because I never changed that until the last.
You change this?
Yeah.
Don't change that.
Oh, I thought.
That's what I'm saying, I looked at mine, but even that was the same. Backwards. Oh, I bet I know what it is.
I see.
I did the exact same thing. I was like, I remember this. There you go.
It's actually not as bad as I But, as, while I'm doing it, just working on the free thing. And for the functions that I have, I'm just gonna pull my references, like, call my reference get content. And call my reference, get right child and left child. For labs 133.
So the space was gonna be roots. It's gonna be, wait, which one?
There's call my reference to the contents and call my reference after.
So your base was gonna be, you have to pass on the note, that's 23?
Yeah, there's 3 call my reference things.
Oh, you just return. Oh, that's weird, no. This is part of the list. You literally just return the private number, so you return the contents.
So it's just the same as this one?
Yeah, exactly. Yeah, just one's over, they're over there. I don't know.
And it's the same for the lights.
Yeah, they're all gonna, yeah, all the ones that have the double, the second one, it's the same as that.
Right, hopefully I have to rent this one.
One person got
Any questions about the public functions versus private functions? We kind of get what they do.
Every time I look online, they use struct to build a node. Use class.
To confuse you? No, because I mean, traditionally, that's just how they get taught, is with structures, but because we have classes, then we don't have to worry, right? We can wrap some things into structures that make it a lot easier. So like in these algorithms, instead of having to create a node, right, via the struct, and then say left child is null, right child is null, every time we create a node, we just have to construct it. It all makes it easier. And it makes it harder to Google it.
Can you explain like you explained it to me once, can you explain one more time, that type def like pointer thing that we created outside of the global scope? And why does that like
So you can say type def anytime to take anything, any type that you have, and you can name it whatever you want. Right? So we can say type def int food. And now everywhere my program instead of saying int x, int y, I can say foo x, foo y. So it just allows us to rename it. You don't really do it with integers, but what happens is that, right, and this goes back to a question on the test that most people got wrong. When I say type def int star as int ptr, right? If I do that, now instead of saying int star, where I can say int pointer, right? Which doesn't really, right? I mean, it's just a shorter, right? I mean, I guess not even short, but just a different way of doing it. But the big reason that a lot of people like doing that is because when I say int star, actually let's do it like this. When I say int star x, y, okay, the star floats, just like the ampersands float and everything like that. So the star floats. So when I do this, x is of type int star, but y is of type int. Which is confusing, I would say, right? You would think, I said int star is a type, shouldn't they both be int stars, right? Integer pointers, but they're not, because you can also write it like this. Both of those mean the same thing, that it like floats. But if I wrap up the star in something else, then when I say, right, int ptr x, y, they're both int stars. Because there's no floating star, right? It's all wrapped up in the thing. So a lot of times that's why people will do it. Yeah, in case you forget, it's a downside. And then, yeah, for me, I like seeing the star, so I know that that's a pointer. And I know it's called integer pointer, but I like seeing the star so I know what's going on. So I don't like that one. And if you just want to make your code look super confusing, you can wrap everything in a type def, right? And then you don't create doubles, you don't create integers, you create
pseudocode?
Yeah, you create whatever you want to call it. Names of all your favorite characters in Harry Potter, right? Could be all your variable types. Not the names of your variables, but the types. Like you could have Slytherin X, and that's about all I know about Harry Potter.
That's it?
There's other ones too, but you could do that with all your variables and make it.
So if I work a job and I don't want AI to be able to replace me, I should just use all type defs.
Yeah, right? Exactly. Exactly.
Well, it's the word you heard is these new nodes.
Yeah,
Okay.
that's.
It's called job security, right?
Your private member is called untraveled, or just like that, right?
Yeah, I think so.
Well, I would say no.
Yeah, okay.
Once again, when you're doing recursion, reach for that. Yeah. So there's something that's right, and maybe
You
even
realize that the set.
You just need to check. You only have to check some names.
No. Where, did these have loaded versions? I don't think they did, but.
Instead of a blue, you could see the names. If
You see if they're wrong, I can try it.
if we're at 0 at the first letter, equal to the last one, we're at. Maybe up to the second one, right? That one says.
Yeah.
This one might be off. So if
Because I want people to charge it as well, but I don't know if there's the overloaded one or.
Well, okay, yeah, so.
we're at 0, right, the first letter.
Yep.
The last letter was that word at.
No, is that what you use for content?
No. You know what, actually, I'm not gonna use.
So if that is true, meaning the first letter and last letter are equal, then you see the.
It does, you do the transaction.
Wait, that's one point three. Because I was looking at the instructions, it's.
So if the word is
Oh, you're right. I talked about it.
else if
It
0.
is the worst thing, it's not.
Maybe I have to. So we'll call word counter. Here we have the concept. So.
It's not, so, you know, it should be contents is zero. You say the right is null. Oh, did you overload the constructor? Yeah, you did.
It's fine.
But you didn't set left and right to null.
Oh, that's wrong.
Yeah.
Minus one's the last one. One moves us forward, so we check the last piece of character, right? So then I want to go forward one, so which is why I want to.
Just, that's how you content.
This was on minus one, so I go minus 2. So that's how you don't want to use my This is by definition, right? That's for my stock condition. If it's empty or it's 1, it's false, right? Right, so that's the stock condition for true. The stock condition for false is if these aren't equal, right? So then you return false. If the outside ones are equal, then I have to call the same function on the subject, the small one, and double check. Is this equal? Not right. They're kind of, I mean, they're kind of just made up, right? They're not really, things that you would do.
It says, called private function, so I identified as I have a public. Then over here, and I'm supposed to, it is supposed to be separate, or is it public?
The public ones will pass in. That's all you have access to. But all the private ones, right? Notice, so in insert, actually, let's go with what they have. So in order, you pass in order root, right? So now in order, this would be subroot. Because it's the right parameter, so the argument's name is root, and here it's going to be sub.
And then do I have to declare the here? No.
On the calls. On the calls, we just pass in the values.
Okay.
Alright, so this is my web development Eclipse Shape project, and you see that terminal, slash projects and slash, so I don't know why this one's not working.
Top of this, little red X thing hasn't, saved, it's,
No, I need something else.
I need to worry about that.
I don't wanna worry
The
about it.
program I run is fine, it's just,
Yeah, well, I mean, you can see the red, so that's what the red, but it's trying to figure out why it's not working.
okay.
Yeah. The little red X's.
Oh, yeah.
I don't know what they mean. It could be that they have like a,
Not saved maybe?
well, no, it's not that. It could be like Xcode does like pre-compilation for you. So it'll look at the code you're writing and try to pick out compile errors without actually compiling. I'm guessing that's what it's doing. Because notice it made things red.
Yeah.
File on the right side. So you can see that's the on the right side.
Yeah, fair enough.
But that exists. I don't know why it's
Oh, because it's in a different location. That's a storage file. I have to copy it, right?
Well, stress test. The stress test, because most of the non-stress tests, we're only going one level down. Here's root, add one on the left. Here's root, add one on the right. Not add one on the left, then add one on the right, then add another on the left. So it's like it's test. It's making sure that when I make a big tree.
That's supposed to be overloaded.
Insert?
Yeah.
It's not overloaded. Oh yes, it is overloaded. A public and a private.
Okay.
Yes, it is overloaded.
Right, okay. So, the public should only have contents, right, and then the private one is section. I'm getting an error saying that there's no function call when you pass in a single thing.
Yeah, so yeah, you go.
But I'm saying, I guess what I'm saying is the public one should only have int, and then the
And
private.
the public one calls insert, passes in that and passes in.
And then you just clearly pass in root.
So the public ones start the recursion and then the private ones are the recursive.
I see, okay.
But we don't need the user to pass in root underscore, right? It's private anyways, they don't have access to it. So they just want to call insert and not worry about, does that make sense?
Yeah.
So we're hiding
It has to be passed in.
Right,
I was gonna say, when you just said it, inside, you can't.
You can't. We don't want them to have access to all the pointer stuff and all of our private. So it's protection for both programmer and user.
So,
All right, and
What day is it? It's like you were to bet money. It's we're very confident. You can just tell the audience back and moving ahead.
they're both would return bool, right? Or do you?
yeah, they're both going to return the bool. But the public one's just going to return the private call.
Return insert.
All right, Luke. So in lab 21 here, I have a problem with template argument deduction, and also it's telling me that it expects 3 arguments, right? And when I set this to the default, which is a apostrophe, right, or comma, what happens is it just completely breaks. And over here in the function,
Yeah, that's good.
I just changed the only things that need to change with the template.
Has value.
And then it's telling me has value, has
right,
value.
Yeah.
Because before I set that default argument, right, it was telling me prepare for display was having a deduction issue.
Okay.
And then,
So, I mean, this is fine. So it's saying has value.
yeah.
Right. Bool has value, t value is n size, t value defined. Has value. Bool has value. But only in that function, huh?
Okay.
So make those the same type.
Yeah.
And then
Okay.
you'll be okay.
2 different functions, different parameter, or different.
That's why it's freaking.
So there's your public function. Your public function has no function. Only has access to private function, which is just. Which is fine. The public one has to include. Right? And then that calls, right? This calls. Right? So when I call in order and I pass in root underscore, it's going to be down here, and subroot's going to be root underscore, right? And then we're going to call it again, and it'll be root underscore left child, or it'll be root underscore right child. And then if it gets called again, it'll be root underscore left child, left child. Does that make sense? But it's going to handle all that propagation down the tree for you.
And then,
So you throw it out, which means that this function in order returns a what? String. And what calls this?
in order what?
Right. Right, which means that this right here, right, that function call is this string that this created, right? But this function also returns a what?
Right, so it holds the number of nodes in the tree, it holds the number of nodes, yeah.
Well, but this is a string, right? In order root underscore is a string, right? So how do I get it out? Right? That's basically saying like, that line of code is, right, 1 space 2 space 3 plus 1 plus 9. Right? That's really what that line of code is. How would I get that out of my function? Well, you don't have to. You just have this.
Oh.
How would I get this string out of my function?
Oh, this.
That makes sense? So I would just say return a string, right? But I'm telling you that this line of code right here is this, right? Because it returns a string. Right? Whatever that function gave you, right, which was a string, I want to go ahead
And move this.
It looks pretty good, right? You're saying add to the string, the whole left tree, a space, where I'm at. And memory address, you're gonna have to do something with that. Space. This is just a pointer to this. You want to get the context.
Oh, like it'll identify all those
Okay, yeah. Or
as long as you're included, right? What is it? C++ or G++, space star, like asterisk, period, period what? CPP. That's all CPP
That's right. You only need to take the Linux class.
I've been trying to force myself to do this for so long.
2 to 4:15 today. You only missed the first, 20 lectures. 25 lectures. Yeah. That's right. You should at least know how to do little things like that. Yeah.
Yeah, for content, yeah. So it's actually going to be overloaded. You need to version, you need a public version.
So for this one, you should have.
For insert, yes. Public version just won't have the node. And then all it does is the public version also.
That's all that you just do. That would be that includes your HTML. And this.
I mean, you pretty much can. Legit.
Sometimes the nice thing, not nice thing, but when you template stuff, you normally get an error for every type that you're in. So like, you get an error saying the version in
But because you're not going to be able to do that, all you're going to do is you need to boost by one. I do it outside of separate functions. So.
It's like a 0 and
Oh, no, it's just this one. But here, like not before.
Yeah, that makes sense now.
The computer's so hard working on files.
Right, yeah, because they're very similar to me.
Yeah. And there's missing little things here and there. I have to count all over mine. I just have to find them out.
Yeah, I think this one's like get left child for the lab, and I think for this time it's just get left.
This thing does have a find and replace thing, it's pretty cool.
Oh, yeah.
You edit all of it at the same time. Or well, I'm doing it now. No, I haven't.
Alright, what do you got?
Oh, right.
Yeah.
Constructor cannot be
Straight in order, right? What's it called? Put a bunch of
Yeah, right? Well, it says DL node CPP and then it says DL node H.
Just the name.
Okay.
Oh.
There it is.
Publication.
Okay. It creates the version that it's root. Yeah. I'm just trying to make sure, like, oh, no, I'm just trying to make sure that this function already has 50 value.
Those types of areas are so hard to do.
Yeah, right.
Something talk for the other. It's very long. point up there, we got the engines on board.
Yeah, yeah. Make sure they're both good.
Values. Less than.
So we're putting,
Thank you, appreciate it. So now, even like, I see you're saying, I need to write more than.
All right, Luke,
Yes, sir.
I need some assistance with precision.
Okay.
So in the templates, when it starts asking for
Yeah.
a double, right?
So see how dot set F and all that fun stuff, right?
It's prepared for display, right? Now, I commented this out because I'm assuming that's probably what I need to do.
So that's half of it, yeah. So
So,
you have to also set F, so the
Well, I mean, I would never.
examples.
But otherwise.
I look at. I'm gonna go with the advanced IO, but yeah, here for now.
oh, Phil.
Not fill, but you need this. So you need the set. You have to set the flags as show point and fixed, and then you set precision. So line 34, and then you already wrote line 40, but you do that one. You need that one as well for the precision.
So that line?
Mhm.
Okay, so that's all I would type here?
Yeah,
Or would it
yeah,
have to be?
but then it'd be ss.setf instead of C. See how we're talking.
Oh, so the name of the string stream, because I named mine compound,
Yeah.
so that.
Oh yeah, whatever. Yeah, whatever the name of your string.
Okay, and that would go before this
Yeah.
precision?
Mhm.
Okay.
And then precision only affects doubles as
Yeah.
those flags. So
Yeah,
so even if because it's gonna output strings and integers and doubles, right? But
Yeah.
only the doubles button precision. Remember, the subroot is a pointer to a BST node. So it points to. So it points to one of these nodes.
Yeah, I don't have any shorts. I have most of it, I've got some copies from the Sun 5, so I have things in there I'm supposed to be there and what is relevant. So
you're in, right, you're pointing to this thing, so you have access to all of these public functions. So let's look at this. I mean, this should make sense, but down here, right, and you say subroot arrow what? Get left child, right? The subroot is a pointer to your node. Get left child is one of your functions, right? That returns, right, a pointer. But we don't want a pointer now. What do we want? We want the content, right? So which function returns the content? Okay, then you have to touch a private variable in content. So in here,
Oh.
or you're not gonna say content subroot. What are you gonna say?
Get content.
Well, get content is a member function. So
you want to continue.
you're not gonna write it one way here and write it totally different. You're gonna write it the same way that you do. Use the arrow.
Basically, so the thing is,
But this works for this.
you make function for function. Nope. So you return insert. So, and that itself returns the grid. So, yeah, so your last one should be like, you have an else if, return, get right child, right? Yeah, so that last one. Yeah. But yeah, the thing is, in 705, you will actually do that. But this one, you're just putting it together. Oh, right. So actually, the last two, right? So the The get back jump and the get back jump are both returns themselves. Yeah. So they're not just, yeah. And I give it a sign.
Hey Luke,
Yes, sir.
how big is the jump to C++ to C?
I mean, it's a smaller jump than from any other language to C.
Is there like, really like, words?
So take what we're doing, right? Get rid of,
you learned.
It's just even more like, not simpler, but like it's simpler in terms of computer, like you have to define everything more, right?
get rid of all classes, Excel structures within classes.
I apologize, a lot of things I was seeing, the double inverse redux, I kept seeing a malloc.
Yeah, it's a malloc is just new.
Yeah,
So the same new is malloc.
but it's like weird, it's like in star, in the parentheses.
Yeah.
The name of the variable, malloc, and then the type.
Yeah, it's just harder. But if you want to like design your own computer chips and then just build them like electrical engineers, computer engineers. That low level stuff.
So, well, it depends on what you're doing. Are you calling the same name?
No, yeah, I need to call this function, which is like a private section.
So if they're the same name, the only thing that differentiates them is the variable was in passed in, correct? If one in gets passed in, it's gonna call that first one. If there's a process, it's gonna that one. So basically, yeah, that's how you do it. So you would, well, first of all, you're returning something, so you need to return.
Oh, sorry.
That one doesn't need to return.
Oh, does it?
No, the structure's not. You're just gonna call the function. This one is gonna need a return though. The insert is you return types of more. Yeah. And then you pass in the contents and root. And that's gonna force it to call the private version.
Use value.
You don't have to initialize with that because you're passing it in, not creating it. So you're passing contents. No, contents.
I use value down here. So.
Oh, it doesn't matter. The scope is this, so I mean, the name doesn't transfer, just the context. And yeah, or it's gonna be root.
I use subroot. Actually, I use both.
Go to your.
Where I did have root here, that's how I use the subroot up there.
Right, well, so subroot is just is what you're going to be calling it inside your recursive functions. But what you're actually passing into it is root. So that's what you're passing in is going to be root underscore. And then in your recursive function of insert, it's going to be called sub. And you're just calling it that. And that's just
And same for clear, clear. Is it the same for void clear?
No, because void or clear itself is there a private version of clear? Okay, then yeah. So yeah, it's gonna be nothing but that. Return it. So actually no, it's a void that we don't need to return. Just call it clear and then pass in your other one. So and this is where you're basically what that algorithm is going to be this thing.
all the easy stuff too.
Because what? Yeah. So what it means that maybe you're not returning something. So you're returning keys, right? But if this case happens, they're not returning. That's the true case, right? You get rid of it. So some check is null, and I would guess since in this one you deal with null, right? And in this one you deal with null. Which one follows null?
I see.
So how many functions do you write? Like main functions, like
Three?
three. Not this one. Not that one. Which one we're gonna do? This is what.
In order?
And in order, if subroot is null, right? Can you subroot get left child? What'll happen?
So I need to do it just so you're not gonna
And that is saying empty string, return empty string is null.
Okay.
Because the function still has to return something, right?
Right. Okay.
We're going forward to backwards.
Okay. Now your final. The very last one.
Which you want, that is,
Like the very last line though, it would be
the array.
Oh, sorry, you just have that up or that's not over there?
So yeah. Yeah, the right concept, right?
Okay. I see, because the other, I see, I was thinking it doesn't. Yeah. I see, the else is make it, so you have the rest of it. Right, you could probably put it on the bottom because of the else is, but doesn't really matter, I think. Okay. Zero.
And yes, and you can't do it. No.
So, sorry, the attention function. The first choice, the also one is the appraisal function. So the first,
Transfer to a several remote. All other type inside any function.
Yeah,
Or it's a business function.
I would only want to return true function.
You're setting
Equal zero.
You can do that on like creation.
Oh, you have a return false.
We can't do it as
Looks cool.
Yes. Especially when you're doing all the topics.
Yeah, so you will need to return. Meaning that you created it?
Yeah, because I was just trying to search it around. I want to do the cool.
So is it return true from, true output?
So they're gonna, so no, what you're gonna do for the else ifs, you actually just return the function itself.
Alright.
And then outside of those else ifs, that's it.
Actually has a function.
So your if statement says if the subgroup is null, what?
Not equal?
Why not be null?
Yes. Okay, that's not, and then I can still keep my else, and I did do the empty thing. Okay,
But you're saying if it's null, go ahead and dereference it and do stuff with it. That's not what you're
that's not what I wanted. I was wrong, okay.
So I'm trying to figure that one out, because I passed everything but import. I passed
Okay.
everything,
Yeah.
insert.
Yeah, you in order has lots of extra space. I mean, look at the numbers. I think the numbers are correct, right?
I think so.
Which means you're doing insert correctly, which means you're doing clear correctly. So it looks like you got ways.
When I put the technology, the space in between right here.
But I didn't like the order.
Oh my God, they're all.
That's why it's not displaying properly.
Think about what, in order it says, output the left subtree, output B, then output the Q. Right. Yeah.
So it's not the most.
Yeah, that's the third line down, right? Subgroup equals new BST. Yeah, but in this function, you're just on subgroup. Right, a parameter subgroup on the top right?
We're really confused, we're like, oh, so we're kind of out there.
Are you talking about root underscore?
Yeah.
Well, that root gets passed in this insert function, right? Which links this parameter, or this argument with that parameter, right? So they are the same thing the first time you call it.
Yeah.
So you should never do big root in any of your functions. It will get passed down. Yeah, so the first time, right? The first time you insert something into your thing, right? You call insert on insert 10. You say insert 10, pass in the root. Well, root becomes subroot, right? Subroot is null, right? Because it's the first time. So subroot's null. So now subroot, which is root, becomes 10, right? And then from then on out, then it starts.
No, we just output the root.
Root is subroot is root. You don't ever want to, in your recursive functions, you never want to think first, like only when the tree is empty, right? You have to think that the tree is made up of tons of stuff.
And then cut off.
If any of those trees, so the algorithm is going to work when root is null, but it's also going to work when you're recurse 5 times, right? And that's null. It's going to be the same. Root is null.
So well, because if you think about it, I'm having again. So I just need to see out actual. So I need to do this first. This function is, yeah, I originally had it right here. Yeah, I get that. I get both of them, I still don't get that.